Okay, all right. Well, today we'll do our first actual real lecture of content, stuff related to the course. I just want to kind of introduce, I guess, some basic machine learning concepts here. All right. We're going to just talk about models and machine learning. Okay, so what is machine learning? Okay, and so if you go to Wikipedia, there's like a whole bunch of articles about machine learning, and it kind of just says machine learning is the scientific study of algorithms and statistical models that computer systems use to effectively perform a specific task without explicit instructions, relying on patterns and inference instead. Okay, so there's a lot to kind of parse through there. But, kind of what I say, the big idea there is that we are going to fit models, statistical models, to the data, okay? And, humans, researchers, still have to make a lot of decisions regarding, which model to use, how to specify that model, and things like that. But a lot of the decisions are guided by the data and the algorithms. So that's this part where it says to perform a specific task without using explicit instructions, relying on pattern and inference instead. So that's the part where a lot of the decisions are guided by the data. And so when we say the decisions are made by the algorithm, that's the machine learning part, okay? Now, it's not magic, all right? You can't just turn off your brain and say, I'm gonna throw a neural network at this and have it give me the answers, okay? That's never a good idea. You as a person and researcher, data scientist, will have to still make a lot of decisions, but a lot of the little decisions can be left to the computer and the algorithm. All right, so let's just talk about, what is a model? So this is a word that we throw around a lot in statistics, and we talk about statistical models, and it's this very important idea. But what exactly is a model? So here I've got a picture of a model airplane, and one way we can think of this is we can say a model is a simplified representation of something complex, right? So this airplane, this fighter jet, is a very complicated machine. The real version is very complicated, okay? And here we have a toy model of it, and it's a simplified representation. And so similarly, when we talk about a statistical model, is that, in the real world, there is some kind of process that generates data, right? There is, if we think about, why are some people tall and some people are short, okay? There's complicated things that go into determining a person's height, genetics, environmental conditions, nutrition, all of that is very complicated. But we can simplify that and just say, you know what, let's look at the height of the parents. Maybe the height of the parents can explain some of the variation that we see in someone's height. So statistical model is a simplified representation of a probably very complex real-world process that generates the data, right? So the process that generates data in the real world is complicated. There are many things that ultimately determine the outcome, and a statistical model is going to be a simplified version of the relationships between the variables in the real world, okay? Oftentimes it only includes a subset of the variables, and there's always an error term to kind of account for everything else that is not accounted for in the model itself. Okay. There's a statement we often say, and that is all models are wrong, but some are useful, okay? All models are wrong, but some are useful. And this is true, especially when we use models for prediction. The models are rarely going to predict anything with 100% accuracy. They're all going to be wrong to some degree. But they can be useful in helping us understand or gain understanding um, uh, the relationships between variables, and they can also be useful still for making predictions, okay? They're not going to be 100% accurate. There's still going to be some error there, but the model will make a better prediction than if we didn't use a model at all, right? And these are often kind of the two priorities that you might have to choose between regarding which statistical model to use. Certain models are really good at making predictions. For example, we'll take a peek at neural networks. Neural networks are really good at predicting things, okay? But if you try to understand how the neural network is making these decisions, it's very, very hard. It's very hard to understand what exactly the neural network is doing. Okay. On the other hand, other models like linear regression, okay, it will explain. You can understand the relationship that forms between variables, and it's going to be very good for understanding the relationships. Its prediction power is usually okay, but generally there's going to be other models that are able to do better predictions, okay? But there's a trade-off there. There's a trade-off. Do you want better predictions? Do you want more understanding? Okay. So for this lecture, we're going to take a look at a data set that comes from the textbook, okay? And some students were asking if they should get the textbook. I'm going to assign some homework problems directly from the textbook, so you know, at least for that you'll need it. I know there are versions of a PDF, you know, floating around on the internet. Please don't link to that on the campus wire. I don't want to you know, promote any kind of copyright infringement stuff on any official course related stuff. But you know, what you guys find, you know, I generally try to choose textbooks that are free or really cheap, and unfortunately I could not find one that I liked enough for this class. And so this is of all of my classes that I teach, this is one where I do have a textbook that you do kind of, that costs money to get. So I apologize for that. But anyway, here's an example that comes from the textbook. And we are looking at data from the Olympics, and it's the 100-meter dash track and field event. And we are looking at the gold medal winning time. And I think it starts off in around 1900, 1896, and goes up to maybe like 2012, something around there, okay? And this is what it looks like. If you plot this, just create a scatter plot, we can see that over time, the winning race times have gotten faster and faster and faster. So for 100 meters in 1900, if you could run it in around 11 seconds, you would have won the gold medal, okay? But today you have to definitely run under 10 seconds, okay? And it's quite a difference, okay? All right, so linear regression, linear model, this is something that you are probably very familiar with already, I'm assuming, from 101A, okay? And anyway, what we're gonna start off, we're gonna just say, you know, the model, okay, is gonna basically say, as time has gone on, the winning time has gotten faster, okay? And therefore, if you know the year in which the Olympic Games took place, you can have a generally decent idea of how fast the winning race time was, right? And if we're going to use a linear model, the linear model says the amount that we adjust when we make our prediction is going to remain a constant throughout the data set, okay? Meaning that if we say the time improves by, you know, 5/100ths of a second between 1920 and 1924, then we're also going to say that the improvement between the year 2000 and the year 2004 is also 0.05 seconds, okay? That's what we are trying to say. We're trying to say that the amount of the change that happens between, you know, any 2 years here is going to be the same change, okay? And that's what it means to have a linear model. if you don't want to say it's a constant throughout all of time, then the linear model is not appropriate, okay? Now, so clearly this is not going to work for predicting values in the distant future, right? Because if you keep decreasing it by 0.05, eventually you're going to end up in negative time territory, and that doesn't make any sense. But it can still be useful, at least in the region where we have collected data, okay? And so for the linear model, there are two parameters that we need to estimate. We need to estimate the slope of the line, and we need to estimate the intercept of the line, okay? And so when we talk about fitting a model, all that means is estimating these model parameters. So, okay, we just need to figure out an estimate for the slope, an estimate for the intercept, all right? And that's all it is when we say we're gonna fit a model, all right? And other models, for example, if you create a neural network, you're gonna have a whole bunch of different parameters. But when we say let's fit a neural network to the data, all that means is let's just figure out the estimates of these different parameters, okay? You don't have a slope and intercept, you have, you know, weight 1, weight 2, weight 3. You have, you know, maybe 60 different parameters, 1,000 different parameters to estimate. But fitting a model is just estimating those parameters. There's nothing special about it. It's just figuring out what's the best slope and intercept to use, okay? Or in whatever model you're using, just some other values. Sorry, let me silence my phone here. Okay, so this brings us to the topic of the objective function, all right? When we fit a model to our data, we want the best parameter estimates, all right? We want the best ones. And so how do we define what it means to be the best, okay? How you define the word best is very important, and that's going to be carried out through what you choose to be your objective function, okay? So in ordinary least squares regression, the best model is the model that minimizes the total squares of the residuals, okay? So the total squares of the residuals, okay, where we say the residual is the actual value, y sub n, minus the predicted value, y hat sub n, okay? We're gonna take the difference, that's the residual, we square it, and we sum that up. And that gives us the RSS, okay? Or the residual sum of squares, or this is what we call our objective function. And we're gonna say the best parameters are the parameters where this total RSS is as small as possible, right? So I'm hoping this is, you know, all review and very familiar to you, but this is just kind of the concept of the objective function. It's a way we're going to evaluate how good is the fit between our model and the data, and we want that fit to be as good as possible, okay? And it's good when this RSS is small, right? And so this objective function is one that we're going to try to minimize, right? Some objective functions you want to maximize, other objective functions you want to minimize, okay? So this is one we want to try to minimize, so we're going to call it a loss function or a cost function, okay? Because in general, you want to minimize your losses, you want to minimize your costs. And so these are going to be called, so this is a loss function or a cost function. So this is your RSS, this is the objective function in this case, right? Are there other functions that you could use to fit some kind of thing? Yeah, okay. If you didn't square this, what would we get if we didn't square this? What if we used absolute values instead? Okay, well, we'd have a different function, right? So in some cases you could say, you know what, I don't want to minimize the sum of squared residuals. Maybe I want to minimize the absolute sum of the absolute values of residuals, okay? That's going to get you kind of closer into quantile regression, and you'd probably actually use median, you know, but anyway, okay. Forget all of that, all right? We're doing ordinary least squares regression. We're going to keep that simple, okay? And so anyway, just in general, machine learning models and linear regression counts as a machine learning model, okay? Now, if you are applying for a job, don't say I know machine learning if the only thing you know is linear regression, but it counts. It counts as a machine learning model because those parameters are estimated using kind of the algorithm there. And so many machine learning models fit parameters just by trying to minimize or maximize some objective function, all right? And therefore, a lot of machine learning problems can be just turned into optimization problems, okay? Optimization problems meaning we want to search for a local minimum or a local maximum, okay? And although this linear regression stuff is review for you, I think it's a good spot for us to start to kind of introduce us to a lot of concepts in machine learning, okay? So that's what we have here, okay? I'm going to try to match the textbook's notation, all right? So I know not all of you have the textbook, but please do try to get yourself a copy of the textbook. And I'm going to try to match the textbook notation, okay? And so what the textbook uses for the linear regression model, it uses the slope is W1 and the intercept is W0, okay? So we've got the linear regression model has a slope W0 and W1. And when we talk about the value that we predict, your y hat is going to be called f of x sub n, because this is basically the function that we're fitting, f of x sub n, using the parameters W0 and W1, okay? The actual values, the y's, are actually called t's in the textbook, okay? So instead of having y minus y hat, we have t sub n minus f of x sub n W0 W1, okay? Is that all right? And then instead of just the total sum of squares, it uses the mean squared error, which is just basically the total divided by n. So we have 1 over n times basically the sum of squared residuals, right? Okay. Why don't you, if you're following along and this is all okay, give me a little green checkbox saying yes. And if I've gone too fast or any of this is confusing, give me a red X no, all right? And I'll try to. Okay. I've got 40 yeses, 41. Okay, so about. Okay, so far no no's. Okay, well, all right. I got 50 something here. Okay, so we'll keep going on then. All right. Okay. A lot of times, this is just a side note, you might hear about RMSE, root mean squared error. It's basically this thing, but you take the square root, okay? And the reason why you might do that is mean squared error, the units are in squared units. So if you're talking about distances, your residual, like if you took your measurement in centimeters, your residual will also be in centimeters, but your squared error will be in centimeters squared, okay? Root mean squared error will take the square root of it, and so your units will be back in centimeters. So there's options to that. But anyway, the value that minimizes mean squared error is going to be the same values that minimize root mean squared error. So a lot of times you hear about RMSE, and that's just what this is. All right, so I imagine in 100B, I think, or maybe even 101A, I don't know which class, you had to derive how to get the parameter estimates of linear regression. Is that right? Okay. And did you guys do matrix notation for that, or did you do partial derivatives for that? Anybody? Anybody just want to chime in on the chat? Matrix notation or partial derivatives or both or whatever? And was it 101A or was it 100B? I don't know. You guys tell me. Partial derivatives. Okay.
Partial.
Okay. All right. Well, so that's going to be kind of the first notation. Yeah. So partial derivatives and 100b. Yeah. Okay. And so this is where we kind of start off. We're going to say here's our RSS that we want to minimize, right? So we've got t sub n, which is our actual value, and our predicted value for linear regression is the intercept w0 plus the slope times the x value, w1 times xn, right? And so the residual is this minus this. We're going to square that. We're going to add that up, divide by 1 over n, okay? And so again, I'm going to just kind of go through this quickly because I'm assuming you guys all took 100b and you did okay with this section. But we're going to try to find the w0 and the w1, okay, that will minimize this function. So we're doing argmin of w0, w1, and whatever values of w0 and w1 that minimize this, we're going to call this w0 hat, w1 hat, right? So we treat our observed data as fixed. The value of the loss function depends on those parameters, w0 and w1. And we want to find the w0 and w1 that minimize this, and that will be our things, okay? So we're going to expand this out, and so you do the algebra, you multiply, and you get this, and this, and this, and this, okay? And, oh, sorry, something happened here. But basically, we're going to take the partial derivatives of this with respect to w0 and with respect to w1. We set those partial derivatives equal to 0, and then we're going to solve for w0 and w1, okay? And so I've skipped over pretty much all of this work. The details are listed out in section 114 in your textbook. Also, I'm hoping, because you took this in 100b, it's going to at least be kind of familiar to you, that when you take the partial derivative of this loss function with respect to w1, this is what you get. You take the partial derivative with respect to w0, this is what you're going to get. And you set those equal to 0, and you solve, and you get your answers, okay? So we can set this equal to 0, we solve. That will give you your estimates of w0 hat and w1 hat, okay? And I'm hoping this is all okay. Either give me a thumbs up in your reactions, or green check mark or whatever if this feels okay. Give me a red X if this is totally not working for you. Okay, so a lot of you guys are giving me green check marks, so that's good. Okay, so one thing that might be annoying, and maybe you had to deal with this or maybe you didn't, is that we've got these summation signs here. Okay, we have these summation signs in the partial derivatives. We have a summation sign in the loss function. Okay, and so this is where working in matrix notation is going to be helpful for us. Okay, because when you do matrix notation, when you take one vector and you multiply it by another vector, okay, the summation is implicit in there, right? It's basically you're going to take you know, each element in the vector and each element in the column, and you kind of multiply them together and you add them up together. That's what it means to do kind of matrix multiplication. So the summation terms can be, we can get rid of those because that's going to be implied in the matrix multiplication. Now, I'm not sure. Some of you might have taken 115A. That's not a requirement for the class. All of you have taken at least through 33A, which is your linear algebra class, okay? And maybe you took that your freshman year, and maybe it's been a long time since linear algebra. So if you have forgotten a lot of your matrix multiplication, you know, what it means to have the, I don't know, just the determinant and things like that, I strongly recommend checking out this playlist on YouTube from 3 Blue 1 Brown. It's an excellent channel. This guy makes math videos. Everybody should subscribe to his channel. They're really high quality stuff. And he's got a really good playlist on linear algebra. There's probably all the videos are around 10 minutes long or so. Well worth your time. So so be sure to watch those videos. Even if you're really familiar with linear algebra, I think it's good to watch these things. I like to watch these. Just like rereading a good book, I like to rewatch these videos every now and then. Okay, this is my Harry Potter. All right. OLS regression with matrix notation. This is what we're going to look at here, okay? So what we're going to do is we are going to change, rather than having the intercept and the slope parameters, W0 and W1 separately, we're going to gather them together in this one 2x1 matrix W, okay? Or we can call this a vector W or matrix W, okay? And one observation, okay? So again, we're doing linear regression. So really, one observation is just an X value, and it outputs a Y value, okay? What we're gonna do is we're going to append the value 1 to the X, okay? And the reason for this is that we want to be able to express the linear regression, which is the intercept plus the slope times X. We want to be able to express it as the multiplication of W times X, okay? And so if I didn't include this 1 here, what would happen is that the terms wouldn't match when I try to multiply them together, okay? But by including the 1, when I can say W transpose, so you can imagine taking W and making it 1 row, 2 columns, W transpose, W0, W1 times 1 and xn is going to multiply to W0 plus W1 xn, okay? So if I express my W like this, and one observation xn, x of n, looks like this, then the value predicted by our linear regression line, which is the intercept plus the slope times x, can be expressed as W transpose xn. Okay, and therefore I can expand all of that, and I can take all of my xn's and make a big X matrix, okay? So the big X matrix is going to be X of 1 transpose, X of 2 transpose, and it's basically going to be a column of 1s and the column of the X values, okay? So the X matrix, the column of 1s and the column of X values is going to be this, and then the observed Y, or the observed T values, the actual values, is just going to be a column of T sub 1 down through T sub n, okay? And so if I do this, then we can show that the loss function, okay, which if I scroll back here, the loss function being the sum of squared residuals, T minus W0, the predicted, T minus basically your predicted value squared, summed up, can be expressed as this, okay? And the work for this is going to be shown on the next slide, okay? So what's important, all right, whenever you work with matrices, I strongly recommend that you write the dimensions of each of these matrices underneath, okay? So keep in mind, if you're taking notes on a piece of paper, just write down what W looks like, what one individual xn looks like, and what your big X matrix looks like, okay? So W is 2 by 1, W0, W1, and X is going to be n rows by 2, okay? N rows, 2 columns, okay? And T is n rows, 1 column, right? And this is going to be important because we want to be able to make sure that all of our dimensions match when we do these matrix operations. That's going to be the biggest thing that, that we need to do, okay? So if I take the matrix X and the matrix W, okay, X is n rows, 2 columns, and W is 2 rows, 1 column, I can do that multiplication, right? Because when you do matrix, you go across the row in the first matrix and you go down the column in the second matrix, okay? And so this lines up. It's n by 2 by 1, and the result is going to be n by 1, right? So I go across and down, across and down, across and down, and we can see when I do X times W, 1 times W0 gives me this, and x1 times w1 gives me that. And I can do this for every row, and I'm going to get a column of n values here. Right? And so again, when you do the multiplication, right? So, you know, as you're doing this, you might confuse yourself and you say, do I write x times w, or do I write w times x? Okay. Well, if you write the dimensions underneath the matrices, okay, you will not get confused over the order that you need to do. Okay. If you don't write the dimensions, it's easy, because x times w and w times x, they look the same, right? We're accustomed to working with just real numbers in one dimension, where the order of the multiplication doesn't matter. Okay. But when you're doing linear algebra and you're doing matrix multiplication, the order is very important. The multiplication order has to be correct. So we're going to do x times w, which is n by 2 times 2 by 1, and that will result in an n by 1 matrix. Okay. All right. Side note: in R, you need to make sure your dimensions line up as well. All right. So in order to create this thing, column of ones and the column of x's, okay, I take my the x values, which is the year, okay, and then I'm going to create a column of ones. I just repeat 1 n times, and to create my x matrix, I'm going to just bind the ones along with the x values, okay, and therefore my capital X matrix, 28 rows, 2 columns, okay. That's going to be basically the equivalent of this. I've got 28 rows, 2 columns. And then as far as W goes, the parameters, right now I just have W0 is 1 and W1 is 1, okay? These are obviously not the correct answers, but I create a matrix out of this, and W is 2 by 1, okay? And because of this, I can now multiply this. X times W, this is how you do matrix multiplication, is percent star percent. X times W works out and results in a n by 1 or 28 by 1 matrix. Whereas if you tried to do it the other way, W times X, W matrix multiply X, it's going to give you this error, non-conformable arguments. This is probably going to be an error that you will see when you do your homework, okay? I'm going to presume that you're going to make a mistake somewhere along the way, and you are going to come across this error, non-conformable arguments. Non-conformable arguments means you tried to do a matrix multiplication where the inner dimensions didn't match, where the number of columns in the first matrix does not match the number of rows in the next matrix. So in this case, W is 2 by 1 and X is 28 by 2. You're trying to do 2 by 1 by 28 by 2, that's not going to work. It's got to be 28 by 2 times 2 by 1. Those inner dimensions have to match. And so if you get non-conformable arguments, it probably means check all of your matrix multiplications, check the dimensions underneath each of those things, and that will help you troubleshoot where you're coming across, where you're encountering some kind of problem, okay? Again, a lot of these things work best when you work on paper first, and you write the matrix multiplications there.
I have a question.
Yes, go for it.
So back in slide 23,
Uh-huh.
So when you're making that matrix W, what does that 1 at the beginning mean?
This is just a placeholder number. Just a placeholder number. Okay. This just fills in the ones. It's going to repeat ones. So right now my W matrix is just 1, 1. Okay.
Oh, okay.
Which is not the correct values. Okay. But right now we're not trying to fit the values. We're just trying to set up what the X and the W's are. Okay. Yeah. Okay. So so the residuals. Okay. The residuals is just this column matrix. Okay. I just take the T, which is a vertical matrix, n by 1 matrix, and I'm going to subtract off XW. Okay. We established XW earlier to also be an n by 1 matrix. And therefore, when you do addition and subtraction operations, you need to have these dimensions match. N by 1 minus n by 1 is going to result in an n by 1. Okay, so T minus XW is this. All right, and therefore, when we create the loss function is each of these things squared. Okay, the residual squared. The sum of the squared residuals can be expressed as take that T minus XW, this matrix, transpose it, okay? And that's going to be the first value is going to be t1 minus the prediction for x1, t2 minus the prediction for x2, all the way up to t sub n minus the prediction for x sub n. That's this thing transpose times this, okay? And we can see that when you do the matrix multiplication, it's going to take this, multiply by this, you get its squared value. Take this, multiply by this, you get its squared value. You go all the way through to the end, you're effectively squaring these things, and the matrix multiplication does the summation for us, okay? And so therefore, we no longer need the summation sign, and we have this, this thing. And so when you multiply this, okay, this is going to be a 1 by n matrix, and this is an n by 1 matrix, which will result in a 1 by 1 scalar value, okay, which is exactly what we want. The loss function, the sum of squared residuals, is one value. It's not a vector, it's a single scalar value, and that's exactly what we get, okay? We can also multiply it by 1 over n, which itself is a scalar value, okay? And so the loss function is a 1 by 1 scalar value, okay? So we can express the loss function as 1 over n t minus xw transpose times t minus xw, okay? All right, is that okay? We're good? Give me a reaction, thumbs up here or something. Green check, thank you for that. Okay, thumbs up, okay. Great, great. All right, so this slide, this is there's a whole bunch of stuff here, okay? Basically, what I want to do is I want to expand this out. So I've got t minus xw transpose times t minus xw. Okay, I'm going to go ahead and clear your statuses here. And I'm going to expand this out, okay? And so I don't know if you remember all of your what's allowed with the transposes and things like that, okay? But you're going to distribute the transpose and you get t transpose minus xw transpose t minus xw. And when you distribute a transpose over a product, xw, what it does is it reverses the order and you get w transpose x transpose. This is all kind of your matrix multiplication transpose rules here, okay? So if it's been a while, brush off your, dust off your 33A linear algebra notes, rewatch that linear algebra YouTube series, okay? And now that I have this, I just multiply, right? So, you know, first, outer, inner, last, that's how you did like multiplication in 8th grade or something. Okay, so we're gonna get t transpose t transpose xw, the inner is w transpose x transpose t, and then the last is gonna be w transpose x transpose xw, okay? And again, I've written down the dimensions underneath each of these things, and the important thing is that when you multiply matrices is that the inner dimensions line up so that you don't have dimension mismatch, okay? So t transpose t is 1 by n by n by 1. T transpose xw is 1 by n by n by 2 by 2 by 1, and so on. Okay, anyway, take your time to work through this slide, okay? In the interest of time, I'm going to kind of just plow through here, okay? Basically, each of these things are going to boil down to a 1 by 1 scalar value, okay? And these two values, t transpose xw and w transpose x transpose t, okay? These are transposes of each other, okay? Like if I take this and I transpose this, I'm going to get this, okay? And because it's a 1 by 1 scalar value, the transpose of a scalar is still the same scalar, okay? So, so I can combine these two things, all right? And so I'm going to get t transpose t 2 times w transpose x transpose t and w transpose x transpose xw, right? I feel like I've done the work here very detailed on this slide, and so if you feel like I'm going a little bit too fast right now, which I probably am, you can always go back and just review this a tiny bit, okay? And take your time working through this. And then I'm going to multiply that whole thing by 1 over n, okay? And here's just a note about how I can combine the two terms because they're transposes of each other and they are both scalars, so it's allowed to do such a thing. Okay, so anyway, this is where we are. We've established this is our loss function, and what we want to do now is we want to take the derivative with respect to w, set that derivative equal to 0, and solve for w, okay? It's much like taking the derivative, partial derivatives, except we're going to take the derivative with respect to a vector, which is maybe something that you have not done yet, okay? And so we're going to do this, okay? We're going to delve into just the tip of vector calculus, okay? The vector calculus gets very complicated, but we're going to just talk about taking the derivative, right? So, taking derivatives is something early on, all right? And so, so let's just a quick review of derivatives, and then we're going to look at derivatives with respect to vectors. We'll see how far we get in our lecture today. I've got 7 minutes left, okay? So if you remember what a derivative is, basically it's the limit as this difference, h, approaches 0, right? You've got a function, you're adding some infinitesimally small value h, you're subtracting off the original value of f of x, and you're going to divide that by h, okay? If you rearrange the terms, you can also say it's the value of h so that this thing, this quantity is equal to 0, right? So if we multiply both sides by h here, okay, f prime of x times h, and we do all of this thing should approach 0 as well, okay? So, so that's what it is for a derivative of a univariate function. Right now we've got a vector, okay? We have the loss function, okay? This loss function is a function, and if we treat the actual values t as fixed and the observed x's as fixed, then this is a function of just one vector, w. W is the only thing that can vary in this function if we treat the t as fixed and the x's as fixed, right? W then is the only thing that's left to vary. And so what we have here is we have a function that takes a vector in n dimensions. In our case, w is 2-dimensional. It's got a slope and an intercept, okay? Our w is n-dimensional, but that loss function takes that input and outputs a single real number output, okay? It goes from n space in real n space to just one value in real space, right? It outputs a single scalar, real scalar value, okay? And if that's the case, then we can say, if you think back, if you look at this thing, this is basically the gradient, okay, is going to be the value where if you add on some little small vector h, it's going to be where the vector is equal, this quantity derives to 0, okay? So you can think of the gradient as kind of a multi-dimensional derivative, okay? It's technically the direction that points in the steepest descent, all right? So let's just talk about what this means, okay? In a practical sense, if you have some vector w in n dimensions, ours is just 2-dimensional, okay? But here we've got an n-dimensional vector w. When you take some function f, okay, with respect to the vector w, it's basically equal to the vector of all the partial derivatives, all right? So, so earlier we solved the linear regression, or I at least referenced solving linear regression using partial derivatives. And we're basically doing the same thing here, except it's going to be in matrix notation, because the partial derivative of a function with respect to a vector is basically the vector of the partial derivatives, okay? So that's what we've got going on here. Okay, so here we go. It says, like the derivative, the gradient points to the slope of the tangent of the graph of the function, and more precisely, the gradient points in the direction of the greatest rate of increase of the function, and its magnitude is the slope of the graph in that direction. So that's just kind of maybe a little bit more of a geometric interpretation of the gradient, okay? Here are a few helpful gradient relationships, okay? And so this is kind of like when you learned how to take derivatives. So if we've got W times X, W transpose times X, and you take, if the function is W transpose times X, the gradient with respect to W of this thing is just X. Okay, so the implication here is that this value, W transpose X, is a scalar, okay? So you've got the function outputs a 1-by-1 scalar, okay? W transpose is going to be, a 1/n row vector, and X is a n/1 column vector or column matrix, okay? And so the gradient of F with respect to W in this case is X, okay? If you have the opposite, X transpose W, the gradient with respect to W is also X, right? What about W squared, basically? Okay, I've got W transpose W, which will also be a scalar value. The gradient of that with respect to W is going to be 2 times W, okay? And then W transpose times some matrix C, okay? You've got some matrix C times W, right? Well, okay, so if W is n/1, if W is n/1, so W transpose is 1/n. Tell me, what is the dimension of C? What is the dimension of this matrix C? Because it's got to be W transpose W, right? Okay, yeah, C is going to have to be n/n, exactly, okay? C is going to have to be n/n, and so if you got W transpose CW, the result of that is going to be C times W, which is going to end up being n/1, but C itself is going to be an n/n matrix, okay? So always underneath all of these things, write down the dimensions in a subscript below, okay? All right, so let me see. Okay, I think we're gonna have to pause here, and we'll pick up right here, slide 35, on Friday. Okay, and so so where we have left off is we have the loss function that we have established earlier. Okay, and what we want to do is we want to take the derivative of this with respect to W. Oh, did we talk about the answers to the quiz? Oh my gosh, thank you guys. I'm the worst. I forgot at the beginning. Okay, so there's 2 questions, and the answers are going to be A and D. A as in apple, and the second question, D as in dog. Okay, so first question, A as in apple, and second question, the answer is D as in dog. Thank you for the reminder to that. Okay, for that. Okay. Question 1, A as in apple. Question 2, D as in dog. Do I post the lecture notes? I will post the lecture notes to CCLE. I will, okay? All right, we'll end here for today. Thanks for tuning in. Hope you guys get rest. And yeah, 11 a.m.'s answers are the same as the 10 a.m. Both 10 a.m. and 11 a.m.'s quizzes are exactly the same. All right, you guys, we'll see you on Friday at 10 a.m. Stay safe, stay healthy out there, and we'll see ya.